For example 3, we're going to do the same process that we did before. So we're going to keep the first equation the same. In the second equation, we're going to make sure that the x disappears. So we have 2x plus 2y minus z is equal to 6. And we want to use that first equation to get rid of the x. So we'll multiply the first equation by negative 2 to make sure it disappears. So we have 2x plus 2y minus z is equal to 6. And that's negative 2x minus 4y plus 4z is equal to negative 2. And we'll add down. The x's cancel. That's negative 2y plus 3z is equal to 4. Okay. And it might be useful here to not keep that y negative, but it doesn't really make a difference either way. So we have a minus 2y plus 3z is equal to 4. And now we need to really fix that third equation. Okay, so instead of rewriting it, we're just going to kind of save some space. And we're going to take that third equation. So we have 3x plus 4y minus 3z is equal to 5. And we need to get rid of the x first. So again, we're going to go back to that top row. X plus 2y minus 2z is equal to 1. And we have to multiply that equation by negative 3 so the x's cancel. So that gives us 3x plus 4y minus 3z is equal to 5. And that second equation is negative 3x minus 6y plus 6z is equal to negative 3. X's cancel. So that's a negative 2y, that's a 3z, and that's a positive 2. Okay. A negative 2y, a 3z, and a positive 2. Now what I want to do is make sure the y cancels. Now, you might be looking at this and already realizing something doesn't look quite right. You're on the right track if you are. And that's okay if you don't notice it yet. You'll see in just a moment. This is a special case. So we're going to take that blue equation, that negative 2y plus 3z is equal to 2, and we're going to use the red equation to get rid of the y's. So what I have to do is multiply by negative 1, so they're different signs. So we have negative 2y plus 3z is equal to 2, and 2y minus 3z is equal to negative 4. And when I go to do this, the y's cancel and the z's cancel. I get a 0 on the left. I get negative 2 on the right. 0 does not equal negative 2. This doesn't make a whole lot of sense here. So we have no solution. Had I gotten 0 equaled 0, then I could have done something a little bit different. Okay. All right, so let's try another example. Again, the first equation stays the same. We're not doing anything to the first equation, as long as it has all three variables. If for some reason it didn't, then I might want to alter it, but I believe all your examples are not going to have that issue. All right, so we'll take equation number 2, and we want to get rid of the x's. So if we're going to get rid of the x's, we'll take equation number 1. We're going to multiply equation number 1 by negative 2. So that's going to give us the blue equation. And then when I distribute the negative 2, that's negative 2x plus 2y minus 10z is equal to 4. And we'll add those down. So the x's cancel. That's 3y minus 6z is equal to 6. And I can multiply by a third just to kind of simplify this a little. So that's going to give me y minus 2z is equal to 2. Okay. Okay. The next thing I want to do is take that last equation here, and I want to try to get rid of the x's again. So 2x plus 4y minus 2z is equal to 8. And when I go to get rid of the x's, I'll use that very top row equation. So I'm going to multiply by negative 2 to get rid of the x's. So the first equation stays the same, or the red equation, I guess I should say. and we have negative 2x plus 2y minus 10z is equal to 4. The x's will cancel. That's going to give me 6y minus 12z is equal to 12. Again, I can simplify, so let's multiply by 1 over 6. And that's going to give me y minus 2z is equal to 2. Uh-oh. So without even continuing this process, I kind of should notice something. I get the same equation twice. So that should be a red flag right away. But let's just finish it off. So we have y minus 2z is equal to 2. And I'm going to take that middle equation. Again, y minus 2z is equal to 2. I'll multiply by negative 1. I'm just kind of going through the motions here to make sure that the y's cancel. Even though I know everything's going to cancel out, it's fine. So negative y plus 2z is equal to negative 2, and we get that 0 is equal to 0. So my system looks like x minus y plus 5z is equal to negative 2. Y minus 2z is equal to positive 2, and 0 is equal to 0. So if we get this, where we're down to no variable there, we would have said that there were infinitely many solutions, but we can be a little bit more specific than this. Okay, so we know that there are infinitely many solutions, and that's not wrong, but we can be more specific. So what we mean is, we can choose a variable, kind of like we had in one of those Algebra 1 problems. We can let z stand for any variable, really. Okay. So any value. Okay. So let's let z equal t. That's a pretty common one that we use, t for usually like time. Okay, so if we go back and replace, then we have y minus 2 times t equals 2, and we'll solve that, which gives us y equals 2 plus 2t. And then for x, we have x minus y, which is 2 plus 2t, plus 5 times z, which is t, equals negative 2. So distribute the minus sign. That's x minus 2 minus 2t plus 5t equals negative 2. So that's x minus 2 plus 3t is equal to negative 2. If I add the 2 over, that'll cancel out. So I'm going to get that x is equal to negative 3t. Now I know this kind of seems silly, like why are we just going to replace a variable with a variable? But there's a reason for it. When I have infinitely many solutions, what that really means is that these are all basically the same line, which is great. They're all crossing at the same line. But I can't just pick any random numbers and put them all together. I need to make sure that if I pick any number for, say, z, that then when I plug it in, it does match up with a specific y and a specific x. And if you think back even into 2 variable, if I have infinitely many solutions, that would have been something like where I had the same line drawn twice. So if I picked any random x, it had to match with a very specific y. I couldn't just pick 2 random numbers, put them together, and call them the answer. So that's why saying something like all real numbers is not necessarily the best way to describe